Okay, this is lesson 7.4 and 5 about annuities. An annuity is a series of payments or investments made at regular intervals. Annuities can be or may be equal deposits, withdrawals, payments, or receipts. The key is equal cash flow in or out at regular intervals. And regular just means consistently repeating at the same interval. There are several different types of annuities based on if the payment intervals and interest conversion periods, whether they coincide. That's called a simple annuity, and that's the type of annuity we're going to look at in this course. If they don't coincide, then it's called a general annuity. That means something like payments are being made monthly, but the interest is compounded semi-annually. All the ones will do, the payment frequency and the compound will line up the same interval. So payments monthly and compounded monthly, you'll see them line up. When payments are being made at the beginning of each compounding period, that's called an annuity due. And when they're at the end of each compounding period, it's an ordinary annuity. And we'll be looking at ordinary annuities. So the only annuities we're doing in this course are simple and ordinary. Something you won't really have to worry about because they'll all be simple ordinary and we'll do them all the same way, but good background. The time value of money is the two different types of annuities we're going to look at. One is future value and the other is present value. In a future value situation, you're adding up all the regular payments and their interest earned to get a future amount. So something like an RRSP, which is a registered retirement savings plan, or an RESP, which is a registered education savings plan. Those are where you're making contributions, so you have a large amount of money in the future. Present value is how much money is at the beginning, and you make payments to either chip away at that balance or you make payments from an account to get that balance down to zero. But the point is, all of the money is in the account at the beginning and it's accumulating interest, and then you're either withdrawing from or paying off. And some examples are mortgages or credit card debt or payments to a line of credit. So again, the only type we're looking at is a simple ordinary annuity. The letters that you'll see are very similar to the letters we use in compound interest. FV and PV standing for future value and present value. I is still interest rate per compounding period, just like in our last lesson. And N is still the number of compounding periods. So familiar. The only thing that's different is R. R is the regular payment amount. So let's take a look at a couple examples. Pont is starting grade 10. He works at Subway and he wants to save for a car. He determines that he can deposit $100 a month into an account that will pay 0.25% per annum compounded monthly. How much will he have when he graduates in 3 years? We're looking at how much money he's going to have in his account in the future if he's making regular deposits. So how much will he have when he graduates? That's telling you that this is a future value question. So the equation we're going to use is the future value equation. And since we're looking for that amount, we're going to use the equation directly as it's written. FV equals R, big bracket, 1 plus I to the exponent n minus 1, all divided by I. And now we look in the question to find out what we know about the right side. We need to be able to fill in R, I, and N in order to solve for future value. So over here on the right, I'm just going to write R, I, and N. And we're going to go through and see if we can get values for those and then substitute them into our equation. And I just realized you can't see that, so I'm going to move my document camera to the left. Back to the question. He's starting grade 10, he works at Subway, wants to save for a car, and he can make regular deposits or deposits of $100 a month. That's our R. Our regular deposit is $100. I is the interest rate per compounding period. So we are 0.25% per year compounded monthly. So just like in the previous two lessons, working with I, we take our interest rate as a decimal, so that'd be 0.0025, and we're going to divide that by the number of times we're compounded in a year. Monthly means 12, so we're going to divide by 12. I'm going to highlight that number, that 12, pretty important. And for n is the number of compounding periods. Since we're compounding monthly, and we're making monthly deposits, we're making 12 deposits per year, and since we're working for 3 years to make these deposits, it would be 3 times 12. I'm going to highlight the 12 again. And 3 times 12 is 36. You can do this math, but you get a decimal, and that decimal, I'm going to write what it approximately is equal to, is 0.002083, and that 3 repeats. When you have a repeating decimal like this, don't round it. Use the fraction. If you get a complete decimal that terminates and doesn't continue, you can use the decimal in the equation. But if you get a repeating decimal or something that doesn't terminate, that's easy for you to type in, and you have to round it, you have to use the fraction or else you'll get an incorrect future value. Since we're compounding over and over and over again, we really got to work on using that fraction. So we're going to use the fraction. We got 100 for our regular payment. We got 36 for our n. Let's plug it in and see what we get. We've got 100 bracket 1 plus my fraction. If you have another method, n's 36, instead of using the fraction, go for it, but don't round that decimal. And it's really important to get good at punching these into your calculator and trying to get them to do it, trying to be able to do it in one step. That becomes a pretty important skill in the financial math because you don't want to have to do any partial rounding. So I'm going to take a shot here. I'm going to make a fraction. 100 bracket bracket 1 plus another fraction 0.0025. If you don't have a fraction button, you can use the ABC button. You can use divide and put it in fractions or put it in brackets. Whatever you need to do to be able to get the correct answer. And let's see how I did. $3613.156, and we'll round up because we're working with money, and the bank would round you up. 3613.16. So if Ponce starts making those $100 deposits in grade 10 at the beginning of grade 10, and he can do a $100 deposit every month, he would have this much money in his bank account, which sounds kind of impressive. However, if we wanted to think and look more closely at this to see how much interest he actually earned, it is quite small. In fact, it's only $13.16. How do I know that? Well, if he's making 100 deposits and he's making 36 of those, that's $3,600 that he's been depositing over those 3 years. The difference in the future value and how much he's been depositing is only $13.16. So my recommendation is maybe he needs to find a better place to deposit that money if he wants to actually earn some real interest. Word question deserves a word answer, so we could say, therefore, he would have $3,613.16 when he graduates. All right, let's try another one. Emma has won the lotto and wants to set up a scholarship to assist SDHS students who would like to study math at the post-secondary institution. at a post-secondary institution. She wants to ensure that a scholarship of $6,000 will be given out for at least 5 years. How much money should she give SDHS now to ensure that this can happen? If SDHS will invest the money at 10% per annum compounded annually. Wow, that's a lot more interest than Ponth was getting in his savings account. Let's do a little bit of math here. How much should she deposit now? That's telling you that we're depositing that money in the present. So we're going to use the present value equation. And since it's not asking for the regular payment, it's asking for the present value, we're using the equation directly as it's written. PV equals R bracket 1 minus 1 plus I to the negative n all over I. And what do we know? Well, we know that we want to be able to take out $6,000 every single year. So if we're putting an amount of money in today and we want to pull out $6,000 every year, that $6,000 is the regular payment. That regular payment that SDHS is making out for that scholarship. And we want to give it out for 5 years. And the account is making 10% compounded annually. So we need I and N. And since we're working annually is 1. So we don't have to divide our interest by anything because it's per annum compounded annually. So that's just 0.1 divided by 1 would be 0.1. 10% as a decimal. And 5 years times per year, so that's just 5. So we've got our I, we've got our N, and we've got our R. Let's plug them in and see how much money she needs to deposit today. 6,000, 1 minus, 1 plus I to the negative N. Oh, I should have been filling that in. Oops. Fix that. 1 plus 0.1 to the exponent 5, negative 5. Key to the present value is that negative. Make sure you get that negative in there. And when you punch it in your calculator, make sure that you use the negative symbol, not subtract symbol, or else you might get an error. Alright, let's try to punch this in our calculator. So we've got 6, I'm going to make a big fraction again. We've got 6,000. 1 minus, 1 plus, 0.1, guess I could have done that math in my head, to the exponent, negative button, 5, and close bracket, and the bottom, 0.1. How did we do? $22,744.72. That's the present value. That's how much Emma should deposit today. So, word question, word answer. Therefore, how much money should she give SDHS now? Emma should give $22,744.72 to SDHS today. And the neat thing about this is that's a pretty big interest rate. And if she had just been giving $6,000 each year for 5 years, that'd be $30,000. But since we can take advantage of this high interest rate and deposit $22,000 now, almost $23,000, we end up saving about $7,000, which is about 1 year's worth of scholarships because we've been earning interest on that balance all the way along. If we're putting money in now, we're going to earn interest so that when we withdraw the $6,000, there's still money in that account earning interest all the way up until the last withdrawal. And the last withdrawal should be exactly $6,000, and that account would have 0 in it at the end. And that's how annuities work in the present value. Both of those examples were set up to solve for the future or present value. Alternatively, I can set one up that asks for the monthly payment. So we're going to set up one, and then I'm going to have you try to solve it. And let's look at number 3. Number 3 says, Tyler wants a 99% in MCR3U and decides to try to bribe Mr. Risebrow. Mr. Risebrow says he has, Mr. Risebrow says he has 5 years to pay him $60,000. That's his bribe. And he will accept quarterly deposits into an account that earns interest at a rate of 2.75% compounded quarterly. What are his monthly payments? Well, he needs $60,000 in 5 years. That amount of money exists in the future. So he has 5 years, I'm going to highlight the important information here, 5 years to pay him $60,000. He will accept quarterly deposits into an account that earns an interest rate of 2.75% compounded quarterly. What are his monthly payments? First off, we have to decide whether this is present value or future value. And when you're solving for payment, you just have to ask yourself, where is the big amount of money? Is the big amount of money now in the present, or will it exist in the future? And since we're making payments into an account, the big amount of money is going to exist in the future. So this is a future value. And when we're working with future value, we use the future value equation. FV equals R 1 plus I to the n minus 1 divided by little I. I said I was going to set it up. We're just going to do the whole question. Let's look at what we know. Well, we don't know R. That's what we want to solve for. So that means we have to know all the other variables, FV, N, and I. And also, we're probably going to have to rearrange this equation so we can solve for R. Well, FV is the 60,000. That's the amount that Mr. Risebrow needs in 5 years to accept that bribe. N would be the number of years multiplied by how many times that deposit's happening, or how many total deposits are going to be made. Well, if it's over 5 years and it's quarterly deposits, that's going to be 20 deposits. And interest rate, since we're 2.75% compounded quarterly, 0.0275 divided by 4. And if I check that, 0.0275 divided by 4, I get 0.01375. I did not divide by 4, I divided by 2 by accident. Let's fix that. .006875. That's better. That's our I. Now we got to rearrange and solve for R, and it's actually not too bad to rearrange this equation. We're going to multiply both sides by I to get rid of the I on the denominator. So we have FV times I, and then this side we have to have R times this big bracket. So to get rid of that big bracket, we would just divide both sides by that big bracket. And that ends up with R, I'm going to switch sides, is equal to this left side, FV times I, divided by the big bracket, 1 plus I to the n minus 1. And that's how we can rearrange and isolate for R. You won't be given this equation. You'll have to be able to rearrange and get it on your own. Now that we can fill in FV, I, and N, we can solve for R. So I'm going to do that up here. R is equal to 60,000 times 0.006875 divided by 1 plus 0.006875 to the 20 minus 1. And let's try punching that whole thing in our calculator. big fraction, we got 60,123 times 0.006875, and in the denominator we've got 1 plus 0.006875, close bracket, exponent is 20, and we are subtracting 1, close bracket. And we end up with a regular payment of 2808.76. Hey, that's almost affordable. Good luck, Tyler. Therefore, Tyler's, oh, it says monthly payment. It should say quarterly. I did not notice that. Quarterly payment is 2808.76. Yes, because remember, quarterly deposits matching quarterly compound. That makes it simple ordinary annuity because they're going at the end of each quarter. That should have said quarterly. That was a typo. So his quarterly payment should be $2,808.76. Okay, one last question. It's about Brianna's parents calculating how much her math degree is going to cost. I need you to try that one on your own. See if you can figure out whether it's future value or present value, and whether you're solving for the payment or the future or present value, and then try to solve for it. You can check your answers on the course website, and that's it for lesson 8.4/5. And in fact, that's the last lesson of the year, so congratulations. You've now completed all of the lessons for MCR3U1. Thanks for watching, and I'll see you, well, next time, I guess.